In 1987, Soviet astrophysicist Leonid Shkadov published a scientific paper in the Proceedings of the International Astronautical Congress describing a device capable of moving an entire star using nothing but its own radiation. Not a novel, not a screenplay, a peer-reviewed scientific paper. Don't forget to subscribe to the channel and leave a like. With us, it's always interesting. The concept is called a Shkadov Thruster. The principle is straightforward. Place a massive reflective mirror on one side of a star, and the asymmetric radiation pressure creates a net thrust. Given enough time, the star moves. Shkadov calculated that a mirror roughly the size of a Type II Dyson sphere, positioned at the right gravitational equilibrium point, could accelerate our Sun by approximately 20 kilometers per second over the course of 100 million years, enough to relocate the entire solar system to a completely different region of the galaxy. That paper was published 37 years ago. It passed peer review, and almost nobody has talked about it since. So today, we are going to do exactly that. We are going to look at what the Shkadov Thruster actually is, what the physics say, and what would realistically happen to Earth, to our solar system, and to life as we know it, if humanity ever decided to move the Sun. Let's be specific about what actually happens. The Sun contains 99.8% of all mass in our solar system. Every planet, every moon, every asteroid orbits it for one reason: gravity. Move the Sun, and every single gravitational relationship in the solar system changes simultaneously. The first consequence is orbital destabilization. Planets don't orbit a fixed point. They orbit the Sun's center of mass. The moment that center shifts, orbital paths begin to change. Scientists calculate that even a displacement of 0.1% of the Earth-Sun distance would alter our orbital period, the length of our year, by a measurable amount within decades. The second consequence is solar radiation shift. Earth receives 1,361 watts of solar energy per square meter, a number called the solar constant. Our entire climate system, from ocean temperatures to atmospheric pressure, is calibrated to that number. A 1% change in solar output caused by repositioning would be enough to trigger a global temperature shift comparable to the last ice age. NASA data shows the last ice age was caused by a change of less than 2 degrees Celsius in global average temperature. The third consequence is gravitational wave propagation. A mass as large as the Sun moving through space would generate detectable gravitational distortions across the entire solar system, affecting not just planets, but the Oort cloud, the Kuiper belt, and potentially sending comets and asteroids into new trajectories toward the inner solar system. And here is the critical detail most people miss. None of this happens instantly. The gravitational effect of the Sun's movement travels at the speed of light. So for approximately 8 minutes and 20 seconds after the Sun moves, Earth feels nothing. The oceans stay calm, the atmosphere stays stable, and then the wave hits. So let's talk about what the Shkadov Thruster actually is, because the physics behind it are surprisingly straightforward. Every second, the Sun releases an almost incomprehensible amount of energy in the form of electromagnetic radiation. That radiation travels outward in every direction equally, which means the net force on the Sun itself is zero. The pushes cancel out. The sun stays put. Shkadov's insight was simple. What if they didn't cancel out? His proposal was to construct a massive parabolic mirror called a statate and position it at a fixed point on one side of the sun. A statate is a structure that uses radiation pressure itself to hover in place without any propellant. The mirror would reflect a portion of the sun's own radiation back at it, creating an asymmetric push. One side of the sun is now receiving more radiation pressure than the other. The net force is no longer zero. The sun begins to accelerate. Now the resulting acceleration is almost unimaginably small, roughly 100 quadrillion times slower than the acceleration you feel stepping off a curb. At that rate, in the first year, nothing moves in any way you could detect. In the first 1,000 years, still nothing visible. But over 1 million years, that acceleration compounds to a velocity of around 0.3 kilometers per second. Over 100 million years, approximately 30 kilometers per second. That is fast enough to relocate the entire solar system to a completely different region of the Milky Way. There is a second mechanism Shkadov identified that makes this even more efficient. As the mirror reflects radiation back toward the sun, it slightly increases pressure on the sun's surface. The sun responds by ejecting mass through an enhanced solar wind. As the sun loses mass, its gravitational pull weakens, and the planets naturally begin drifting outward into wider orbits. The solar system expands as it moves. The engineering requirements are, of course, extraordinary. The mirror would need to be constructed at a scale that is currently incomprehensible, larger than anything humanity has ever built by a factor of billions. But from a pure physics standpoint, there is no law being violated, no perpetual motion, no exotic matter, no faster than light travel, just radiation pressure applied asymmetrically over geological timescales. Shkadov's paper did not propose this as science fiction. He proposed it as a long-term survival mechanism, a way for a sufficiently advanced civilization to escape an aging star, a nearby supernova, or a catastrophic collision course with another stellar object. Which raises the obvious question: how advanced would a civilization actually need to be to build this? To answer that question, we need to talk about the Kardashev Scale. In 1964, Soviet astronomer Nikolai Kardashev published a paper proposing a way to classify civilizations, not by their culture, their history, or their technology, but by one single metric: energy consumption. His argument was straightforward. The more energy a civilization can harness and control, the more it can do. Energy is the universal currency of capability. Kardashev defined 3 types. A type 1. Civilization controls all energy available on its home planet. Every volcano, every ocean current, every ray of sunlight hitting the surface, fully captured and utilized. For reference, Earth today consumes roughly 100 times less energy than what a true Type 1 civilization would require. By most calculations, we are currently sitting at approximately 0.73 on the Kardashev scale. We are not even Type 1 yet. A Type 2 civilization controls all energy output of its home star. Every single watt the sun produces, captured, directed, and used. This is the level at which a Shkadov Thruster becomes a realistic engineering project. Not easy, not soon, but physically possible. The most commonly proposed structure for achieving Type 2 status is a Dyson sphere, a megastructure that surrounds a star and captures its entire energy output. Shkadov's mirror is essentially a partial Dyson sphere with a directional purpose. A Type 3 civilization controls all energy output of its entire galaxy. Hundreds of billions of stars, fully harnessed. At this scale, moving a single star is not an engineering challenge. It is routine maintenance. Here is what makes this relevant. Kardashev proposed his scale the same decade humanity first reached space. He was not writing fantasy. He was writing a framework for what comes next. A roadmap for civilizations that survive long enough to think on geological timescales rather than human ones. And the critical detail is this. The gap between Type 1 and Type 2 is not just technological. It is psychological. A Type 2 civilization has, by definition, decided to commit to a project that will not be completed for thousands of generations. No single person alive when construction begins will live to see it finished. No government, no company, no institution, as we currently understand them, would survive long enough to see it through. Which means the real question is not whether we have the physics to move the sun. Shkadov already answered that in 1987. The real question is whether we have the patience. So we have established that moving the sun is physically possible. The next question is the one that actually matters. Why would we ever need to? There are 3 serious scientific scenarios where relocating our solar system stops being an abstract thought experiment and becomes a genuine survival question. Scenario 1. Stellar collision. The Milky Way and the Andromeda Galaxy are currently moving toward each other at approximately 110 kilometers per second. In roughly 4.5 billion years, they will collide and merge into a single elliptical galaxy. Now, galaxies are mostly empty space, so the collision will not destroy stars the way 2 objects physically crashing would. But gravitational interactions during the merger will throw stars into completely unpredictable new orbits. Stars that have maintained stable positions for billions of years will be scattered across the merged galaxy. The probability of our sun passing dangerously close to another star during that process increases significantly. A Shkadov Thruster, started early enough, could move the solar system to a safer region of the galaxy before that merger reaches its most chaotic phase. Scenario 2. The sun's natural death. In approximately 5 billion years, the sun will exhaust its hydrogen fuel and begin expanding into a red giant. During that expansion phase, it will grow large enough to engulf Mercury, Venus, and almost certainly Earth. The oceans will evaporate. The atmosphere will be stripped away. The surface temperature will rise to several thousand degrees Celsius. A civilization that has existed for 5 billion years and sees this coming has, in theory, 2 options: move the planets outward or move the sun itself. A Shkadov Thruster could, in principle, adjust the sun's position relative to the planets, buying time for either evacuation or more permanent solutions. Scenario 3. Gamma ray bursts. Gamma-ray bursts are the most energetic explosions in the known universe. A single gamma-ray burst can release more energy in a few seconds than the Sun will emit over its entire 10 billion-year lifetime. If one occurred within a few thousand light-years of Earth and was pointed in our direction, it would strip away the ozone layer completely, exposing the surface to lethal levels of radiation within minutes. There is scientific evidence suggesting that a gamma-ray burst may have caused one of Earth's mass extinction events approximately 450 million years ago. We cannot predict them. We cannot stop them. But a civilization capable of moving its star could, over millions of years, navigate the solar system away from regions of the galaxy where gamma-ray burst activity is highest, toward quieter, safer stellar neighborhoods. 3 scenarios, 3 different timescales, 3 different threats, and in each case, the response is the same. A civilization that thinks far enough ahead and builds accordingly. So let's bring this back to the present. We are a civilization that has existed for roughly 300,000 years. We have been doing serious science for approximately 400 of them. We reached space 67 years ago. And in 1987, one scientist sat down and mathematically described a mechanism for moving our entire solar system across the galaxy, using nothing but physics we already understand. That is an extraordinary thing to sit with. Every civilization that came before us, the Egyptians who aligned their pyramids to the stars, the Greeks who mapped the cosmos with nothing but geometry and patience, the Romans who built infrastructure that lasted 1,000 years, they were all thinking on timescales longer than themselves. They built things they would never see finished. They made decisions for people they would never meet. The Shkadov Thruster is that same impulse, taken to its logical extreme. It is not a weapon. It is not a monument. It is an insurance policy for a species that has decided it intends to survive, not for centuries, but for billions of years. Here is the uncomfortable truth. The physics work. The math works. The only thing that does not yet exist is the will to think on that scale. Every problem humanity currently faces, every political conflict, every resource war, every existential argument about who controls what, becomes completely irrelevant when measured against a 100 million year engineering project designed to keep our solar system alive. The question Shkadov was really asking in 1987 was not technical. It was philosophical. Are we the kind of civilization that thinks past next year, past the next election, past the next century? Because the universe does not care about our timelines. Andromeda is still coming. The sun is still aging. Gamma-ray bursts are still firing across the galaxy in random directions. The threats are real. They are documented. And they operate on timescales that make human history look like a single frame in a very long film. We are, right now, at 0.73 on the Kardashev Scale. Barely type 1. The gap between where we are and where we would need to be to build a Shkadov Thruster is almost incomprehensible. But 300,000 years ago, our ancestors were living in caves. And 67 years ago, we left the atmosphere for the first time. The trajectory is there. The question is whether we stay on it long enough.